We have looked at the morphology of the seafloor from the coast to the abyssal plain and to the processes moving water masses. We're now ready to look at how these interact with the sediments which are being transported by the rivers to the sea. In this clip, we will provide some initial answers to questions such as how are these sediments reworked? Where will they end up? Do their properties change during this stage? What will be the special architecture? We will begin looking at coasts away from deltas or estuaries, and which are dominated by the action of tides. This means that waves are of subordinate importance. Tides cause change of sea level and thereby a gradual transgression and regression of the water covering the intertidal domains. The width of the area covered and uncovered during tides is a function of the height of the tide and the steepness of the coast. In cases such as the famous one you see in the picture, it can be of several tens of kilometers. In the map view, we can see the phenomena associated with the rise and fall of sea level driven by tides. By rising sea level, the water mass will gradually move towards the coast, passing through tidal inlets and eventually invading the entire intertidal zone. This process is generally gradual and relatively slow with only limited sediment transport or reworking. When peak tide passes and sea level decreases, waters will retreat towards the sea. They will do this not in the same homogeneous way they did while rising, but rather getting concentrated in narrow flow paths. Because of the narrower paths, velocity will increase and tides become erosive, forming a network of channels and bringing sediments back to the sea. This is then what the tide-dominated coast looks like. The wide intertidal zone is characterized by marshes and standing waters, typically with fine-grained sediments and very active biologic communities. The tidal channels are a distinctive feature of the tidal systems and accommodate the movement of waters and sediments to the sea and backwards. Tidal barriers and inlets form the last important features typical of tide-dominated coasts. Coasts in which waves are much stronger than tides look very different. We have seen how waves break when the seafloor shallows to less than half of the wavelength of the incoming wave. The breaking of a wave is a very high energy process, which mobilizes large amounts of sediments, which are then transported and dumped in linear features along the coast as the water slows down, coming then to a still stand. In map view, you can see the waves breaking and depositing sands in sandbanks and slowing down reaching the coast. Having hit the coast, the water set moved by waves will return back to the sea, focusing channelized flow along called rip currents. These are strong currents able to bring sediment back to the sea. The entire process starts again with the seafloor being constantly remobilized by breaking currents. This is what simplified wave-dominated looks like. Elongated ridges and barriers, often also submerged. Behind these regions, a more protected domain with bodies of sand transported by the breaking waves. Winds and waves do not always move perpendicular to the coast and are often oblique to it. In this case, waves hitting the coast are deflected, giving rise to a component of movement parallel to the coast itself. These are called along-shore currents, which can erode, transport, or deposit sand along the coast. Walking along the coast, you see typical effects of along-shore currents, such as coastal groins and spits. In the steep coast, the wave hit with her full power the cliffs with a strong erosive energy. As a result, the foot of the cliff is eroded, causing the collapse of the overlying rocks and the retreat of the cliff face. An abrasion surface is created. Steep coasts are very different from flat and shallow coasts. The coastal domains areas are regions of great scientific and technical interest, are areas of great importance, economic importance too. We are now ready to make the next step of our journey. In the next clip, we will enter the wide continental shelves. After having escaped a number of traps in the floodplains, the deltas and the estuaries, and the coastal domains, The sediments, very much change their properties, enter the continental shelf. They enter a very different domain, a large area with little morphological changes, a little lateral confinement. In this clip, we will see how these sediments are modified, distributed, and deposited marine currents on the continental shelf. The very apparent flat morphology of continental shelves and the associated sedimentary processes can only be understood considering the effects of recent glaciation and associated sea level changes. This is what Europe looked like something like 15,000 years ago. Large glaciers and, as a consequence of the low sea level, large domains which are presently underwater were emerged. These are the future continental shelves. At high latitudes, glaciers were present, eroding and transporting towards the plains all sorts of sediments, typically poorly sorted and immature. Particularly when glaciers began their retreat, large amounts of sediments were deposited, ready to be transported away by rivers. Little vegetation was present, mechanical erosion was dominant. Rivers formed wide valleys, transporting the poorly sorted sediment to the coastal domains and further towards the sea. And there deposited sediments in prograde delta systems close to the shelf edge. Clearly, the area of the future continental shelf was characterized by a remarkable variety of sediments in terms of amount, type, composition, and distribution. This has a major impact on the kind of sediments dispersed in the continental shelf. With the improvement of climate conditions, sea level began to rise. In most places, sediments input from the rivers was insufficient and water depths of several tens of meters deposited. Marine currents, tides and waves started moving around, distributing sediments, the coarse and fine-grained sediments which were deposited during the lowest end phase. In the slide, you see a map view of the North Sea and surrounding regions. The light blue colors are indicative of the shallow depths of the continental shelves. Current, whatever their origin is, are generally able to circulate freely. On the other side, however, in regions where, as the one between the United Kingdom and France, where the continental masses allow only a narrow passage, currents can be deviated and water velocities will increase, removing fine-grained sediments and leaving the coarse-grained deposits behind. On the map to the left, you can see the currents in the North Sea region, strong currents in these narrow zones. The map on the right shows the percentage of coarse-grained sediments, gravels in this case, found on the seafloor. There are a few important observations which you can gather from the map. First, there is quite some gravels on the seafloor. As we have seen, they were deposited during glacial times. Secondly, these bodies of coarse-grained sediments are not directly related to the position of present-day rivers and are rather controlled by the speed of the currents moving on the shelf. Speed of the water current exerts also a strong control on the architecture and spatial organization of these sediment bodies. Continental shelf deposits, such as the ones we have been discussing until now, are of the greatest importance in hydrocarbon geology. As you can imagine, you need to have a very good knowledge of these processes if you want to make meaningful predictions of the properties of your petroleum system. If substance is strong, then very large thickness of sediments can be stored in the continental shelves, up to several kilometers. Some of the sediments parked on the continental shelf, however, will not remain there forever and will be transported to the deep sea. We will see this in the next clip. The deep sea, the oceans, huge domains at depths of thousands of meters, cold with little light and only slow water movements. Still, a very important domain for sedimentary systems. What processes are taking place there? What kind of sediments do we find? Do you remember the topography of the Earth? We've seen how more than 50% of the Earth's surface lies at around 4,000 meters water depth. These are the abyssal plains, huge domains, of which we know very little. You've seen this slide before. It shows the four main components of the marine domain: the coast, the shelf, the slope, and the abyssal plain. A domain of key importance is the photic zone, which corresponds to the water column which can be penetrated by light. In this water mass, photosynthesis is possible, and huge quantities of microorganisms, mainly plants, exist called nanoplankton. The nanoplankton forms the first ring of a full food chain, which eventually makes it possible for large organisms to live, such as whales and sharks. Once they die, all these organisms will start sinking through the water column. The soft parts will be oxidized, consuming oxygen and producing a low oxygen layer. The hard parts will be preserved and further sink to the bottom of the ocean. Most of these hard parts are composed of calcite or aragonite. In some cases, they are composed of silica. The trip to the deep ocean floor, however, is not devoid of problems, as with decrease in temperature and increase in pressure, ocean waters become more aggressive and start dissolving the sinking shells. The depth at which all calcite grains and shells are dissolved is called the calcite compensation depth, and is comparable to the snow-slope line in the mountains. In areas where the ocean floor is shallower than the CCD, a fine-grained calcareous mound is found called calcareous ooze. Sediments on regions deeper than the CCD will be quite different and essentially composed of the siliceous parts of the organism and of the clay minerals we will discuss in the next slide. The other major component of the background sedimentation is formed by the clays and very fine sand grains transported by the winds blowing across the larger desertic domains of the continents. Brought by storms, these light and flaky minerals can travel thousands of kilometers, eventually landing on the surface of the ocean and starting their very slow trip to the ocean floor. Similar to what we've seen for the organism derived from the photic zone, clays will very slowly sink and form sedimentary succession characterized by very low sedimentation rates. These are called pelagic sediments. Pelagic sediments, once they've been lithified, are fine-grained, homogeneous, and very well stratified. Limestone-rich sediments are often white. Silica-rich pelagic sediments are often more colorful, partly because the fact that they lie a long time on the seafloor and are thus oxidized. If you look in detail, you can see different softer material between the reddish layers. These are the clay-rich sediments which were blown by the sediments. But sedimentation in the deep ocean is not always calm and monotonous. Once in a while, the quiet is disturbed by the catastrophic arrival of sediments from the shelf. Within a very short time of days, a huge amount of sediments are delivered to the deep basins. These sediment-loaded currents are called turbidity currents and are completely different from the background sedimentation we have described until now. Possibly the first time when these catastrophic events were documented was in the New York offshore, when, with no apparent reasons, the telephone cables laying in front of the New York coast successfully broke. Correlating the break-in time with the distance of the cable, it was determined that the cause of the failure must have traveled down deep with velocities up to 70, 80, or 90 kilometers per hour. Seafloor images have then shown that the current was associated with the deposition of large amounts of sediments. The currents responsible for the New York failures and transported sediment to the continental shelf, to the deep basin, we said are called turbidites. Turbidity currents are generated by instabilities at the shelf and the shelf edge, by which large amounts of sediments are mobilized. Loaded with the sediments, the turbidity current has a density larger than the surrounding water mass and can therefore travel fast along the slope. Eventually, when it reaches the sea abyssal plain, the gradient decreases and the section increases, resulting in a lower velocity. This leads to the deposition of the sediments. In the map view, you can see the different domains and the associated processes. The first order feature is the fan created by sediment transported by the turbidites in the abyssal plain. The shape of the fan recalls in some aspect the alluvial fans we have seen in previous clips, but the dimensions are much larger, often several tens of kilometers. In the upper part of the system, the turbidity currents move fast along the continental slope. Velocities are high and no sediments are deposited. In some places, erosion is important and canyons are formed. Close to the mouth of the canyon, sediments are being deposited and they will show channels and erosive features. Far away, full in the abyssal plain, sedimentary layers will be continuous and with constant thicknesses for kilometers. Indeed, a much quieter environment. And now, let us look at what turbidite deposits look like. Sedimentary layers deposited by turbidity currents have a typical organization called Bauma sequence. This includes great descents at the bottom, followed upward by massive beds, by laminated and covulate sands, eventually capped by the hemipelagic mud. These muds represent the background sedimentation deposited between one catastrophic event and the other. Turbidity currents are generated by instabilities on the continental shelf and slope and occur at fairly regular intervals of maybe hundreds to thousands of years. With geological time, they form thick succession, developing succession implying thousands of catastrophic events. As you see, the deep abyssal plain is not always as quiet as we expected.